doing chapter 10 today, and this is DC circuits. DC means direct current circuits. Okay, so we will learn. So our goal will be the following. So we'll have circuits like this. So here's a circuit that has multiple voltage sources and several elements. Okay, and what we will be interested in is finding the current through each element. Why do we want to find the current through each element? Yep.
Can you find the resistance of each?
Well, that'll be given.
Then the total voltage.
So, yeah, this will be given, and in circuits like this, you want to find the current through each element. Why?
So it doesn't get too much and bright.
It tells you how brightly it will glow. It'll tell you how fast your pizza will cook. Okay, so you want to know the power delivered to each element. Okay, so that will be solving this circuit. Yeah. And if you have multiple sources and multiple networks like this, I mean multiple loops like this, you'll need two rules. These are the two rules. We'll come to that. And those are Kirchhoff's rules. You'll need those two rules to solve this circuit. So solving a circuit means finding the current through every element. Okay? And these are the two rules. And based on these two rules, you'll do an entire course, a circuits course, just on those two rules. Okay? And that's what we're going to study. All right, so DC circuits. What is this guy? So here's a circuit. So it's a slightly more complicated circuit. And again, for this circuit to work properly, when you're designing this, you'll have to know the current through each element. Okay. Do you guys know what this might be doing? Okay, this circuit is fit in there. Here's the input from your phone. Okay. And here's the output to your speaker. Yeah. So what might this be doing? The phone is sending a signal like this. This is current versus time. Okay. That current amplitude is too small, and that needs to be amplified before you feed it to the speaker. Okay. So what the speaker wants is this guy. Okay. This signal looks like it has more energy in it. We know there's no free lunches. So where is that energy coming from? You got to feed it energy, so it's connected to the battery. It's drawing power from the phone. Okay, so this is an amplifier circuit. It's amplifying the signal. Okay. What's the difference between a good and a bad amplifier?
Efficiency.
Huh?
Efficiency.
Precision.
Yep. Okay. You want the signal to be, you want the exact same signal. Okay. And just amplify. Okay. So, what is the word? Fidelity. Okay. So you want an amplifier to maintain fidelity. So that's, anyway, so what we are learning is, okay, so we will learn about solving circuits, and solving a circuit just means finding the current through every element, okay? Hey, Jaden, come on over here. Hello there. You go sit in the corner there.
Sit in the corner?
Sit in that last seat there.
Why?
Because I'm saying so.
Is there a reason?
Yes.
What's the reason?
The reason is you're not paying attention in class, and then you're talking to other people. You're
I
disturbed.
didn't say a word.
Okay, just go sit there. You want to be in this room? Go sit there. All right, so here's a battery. We've seen this circuit before. Here's a battery, here's a load connected to it. And what the battery does is it establishes an electric field in here. Okay. And so the electric field points in the direction of decreasing potential. And here's the potential profile. Okay. So there's not much of a potential drop along wires because the resistance is very minimal. And here's, so if this was a 12-volt battery, that means there's 12 volts there, and this is 0 volts. Okay? And so if you have a positive charge, the potential energy of the charge is the charge times the voltage. So it has high potential energy here. It's lost all its potential energy. Why did it lose all its potential energy?
It was used to operate whatever device.
Yep. So it converted that energy into whatever it was that the device did. Okay. And then it's come back here. The charge has lost all its electrical potential energy. And what the battery did was it converted some of the chemical energy to potential energy and raised it back. And then the charge can keep doing the same stuff over and over again. Till when can it do that?
The battery runs out of energy.
Till the battery runs out of chemical energy. That's it. Okay? All right. So all batteries have internal resistance. Okay. So when you go buy a 1.5 volt battery, that's the maximum voltage it can provide. Then a battery has internal resistance. Okay, so now you connect a load to it. So here's the battery, here's the internal resistance, here's the load. Okay, and then it drives a current, and you'll understand this expression more later in the chapter. But anyway, here's the current, and it turns out, okay, so what you see is the outside voltage, the voltage, that's where you're connecting your lamp or whatever. The voltage you see here is the maximum voltage that the battery can provide, called the EMF of the battery, minus the current times the internal resistance. So when they sell you a 1.5 volt battery, you're not seeing 1.5 volts. You're seeing 1.5 volts minus some little thing. So if the internal resistance is equal to the load, what you're seeing is, instead of 1.5 volts, you're seeing 0.75 volts. So that's what you're seeing. So what does a dead battery mean?
No chemical energy left.
So here's another way to look at it. Dead battery means there's no chemical energy left. It also means the internal resistance is gone to infinity. So if this becomes infinite, any small amount of current, this minus that would be 0. So that's a dead battery. Okay. So that's another way of looking at it. All right, so this voltage, what you see outside on the battery is called a terminal voltage. Yeah. And it's always less than the maximum voltage that the battery can provide, which is known as the EMF of the battery. So the current is the EMF of the battery divided by the total resistance in the circuit. This is a series combination, and when you have resistors in series, you just add the resistors. The power delivered is EMF times I. EMF is the maximum voltage times I. And it's also I square. EMF is I times the total resistance, so it's I square R. So if you distribute that, it's I square R plus I square little r. Okay, so the power delivered by the battery, that's the energy delivered per second. This is the energy dissipated in the load. This is your useful work. What is this?
Oh, we're lost to the internal.
That's the wasted energy lost to the internal resistance. Okay? So let's say if this is 10% of that resistance, then you're losing, if this is 10% of the total resistance, then you're losing 10% of the power. Okay? If this is 50, if this is 10 ohms and that's 10 ohms, you're losing half your power. Okay? All right. So here are resistors in series. So when you connect bulbs like this, they're connected in series. And the total resistance is just the sum of the resistors. Okay? When you connect elements like this to a battery, the current flowing through the resistors is the same. Here are resistors connected in parallel. When you connect resistors in parallel, okay, each resistor sees the same voltage. Okay? So like I said, all our devices in our house are connected in parallel. Okay, do you guys see, why would you connect everything in parallel in your house? Why connect it like this and not like this? Mm-hmm.
So if something breaks, it doesn't cut the power to everything else.
That's right. If something breaks here, there's no power to this guy.
Why they changed how they made Christmas trees?
Okay, so good question. Okay, so our question is the following. Christmas lights used to be, strings of light used to be like this. Yeah. And when one of the lights went out, the whole string went out. They're still connected like this. But one of the lights can go and it still works. So what's going on? How did the engineer solve that problem?
Have like a main wire.
Huh?
They have a main wire that goes through the whole thing, and then each light is connected to. Each light makes its own circuit with that wire.
So the main wire would have to have a lot of resistance for the current to go through there. So here's what they figured out. Okay, if you look at the bulbs closely, here's the wire, and here's the element that lights up. And when a bulb goes bad, this thing melts. Okay, and okay, the way they designed it, when it melts, these two guys connect.
Okay.
Okay, so even in dying, they're completing a circuit. Yep. And so that's how they. All right. So, so to solve that problem, if one thing dies, how do you deal with that? Okay. So, whenever you want that every object to work independently, you always connect them in parallel. So every device, every plug is a parallel connection. Every house connected to a grid is a parallel connection. Okay. So, and Sophia beat you. That is shameful.
What the heck? Why are you sitting up here?
Yeah. So, the other advantage is that every device is seeing the same voltage. Okay. So, and so on. Okay, the equivalent resistance is 1 over R1 plus 1 over R2. Okay, so when you connect in parallel, okay, so this guy's positive, this guy's positive, and all these guys are positive. So this number has to be bigger than any one of them. So this number has to be smaller than any one of them. So the equivalent resistance in parallel connection is always smaller than the every element. Here's a fun problem, and I'll give you $1 if you solve it on your own. So here's an infinite ladder of 1 ohm resistors. You find the value of this resistance and I'll give you $1. I'll give you a clue. It's between 2 and 3 ohms. Okay, so you just saw that if you connect resistors in parallel, the equivalent resistance is smaller than any one of them. Okay. So here's a 1 ohm resistor, and whatever this resistor is, parallel combination, it'll be less than 1, assuming that's greater than 1. I've already given you a hint. So this is 1 plus 1, 2 plus something greater than 1. So anyway, the resistance is between 2 and 3 ohms. So if you can find that. The solution is quite beautiful, actually. Yeah. Okay, now we'll study Kirchhoff's rules. Okay, so what we want is you'll have circuits like this with multiple loads, multiple elements, and multiple sources of power. And what you want to do is find the current through each element. Yep. And that's solving the circuit. Yeah. All right, so the first rule is the current rule. What the current rule says is the following. Okay, by the way, here's an arm in the circuit. An arm is a continuous connection of elements. Here's an arm, here's an arm. When more than 2 arms meet, that's called a junction. So this is a junction. So this circuit has 3 arms and 2 junctions. And the first rule is the current flowing into a junction is equal to the current flowing out of the junction. And that's a very simple rule. If currents are flowing in, charges are flowing in, and charges do not collect anywhere. So if charges are flowing in here, that's how much charge must flow out. Okay, and that's the junction current rule. So according to this rule, I1 and I2 are flowing in here, and I3 is flowing out here. So I1 plus I2 should equal I3. Okay. What does it mean when you're asking to solve the circuit? You want to know the current through each element. So you want to know current I1, I2, and I3. Okay. So you have 3 unknowns, and what you need is 3 equations to solve this. So here's one equation. Now, if you apply the junction rule to the other end of the same arm, you'll get the same equation. So if you applied it here, I3 is flowing in, and I1 and I2 are flowing out. So you get the same equation. So you only want to apply the junction rule to one end of the arm. The other end will give you the same equation. Okay? All right. The second rule is the voltage rule, sum of voltage rules. Okay, now before I do this, let me give you a sort of a parallel example. All right, let's say here's a mountain. You start a hike here. You go around a loop and come back. What is your total elevation change?
0.
0. So you went, this part of the journey had a certain elevation change here, was an elevation change here. Okay, but the sum of the elevation changes will be 0. Okay. So similarly, okay, if you go around a loop, there'll be a change of voltage across each element, change of voltage across this element, plus change of voltage across this element, plus change of voltage across this element, plus change of voltage across this element, and when you come back to your starting point, the sum of changes of voltage should add up to 0. And that's the voltage rule. Okay. So you go around any loop, and the sum of voltages should add up to 0. Yep.
What is the rule, or sorry, what is the word under the summation sign right there?
Oh, I going around a loop.
Oh.
All right, how many loops does this circuit have? 2, 1, 2, 3 loops. Okay. All right, remember to solve this circuit, how many equations did you need? 3 equations. And so this rule, the current rule, is the easiest to apply, and you'll always have enough loops to get as many equations as you need to solve the problem. Okay. So when we solve the problem, you'll see this. Okay, so you'll see the solution. All right, so these 2 rules, the 2 Kirchhoff's rules, allow you to solve these circuits. Okay, so now, which way does water flow?
With gravity.
Downhill. It flows downhill with gravity. Okay. Current flows in a direction in which voltage decreases. Okay. So if you go against the current, the change in voltage is positive. Okay, so you're going from lower to higher voltage. And when you're going with the current, you're going from high to low voltage, so change in voltage is negative. Okay. So that you have to be aware of the sign of that. Okay, so by the way, that's a typo in the book. That should be VB minus VA. Anyway, all right. So if you're traveling with the direction of the current, the change in voltage is, see, going from high to low voltage, so it's negative I times R. Okay. If the current is flowing this direction and you're going in that direction in that loop, you're going against the current, and so the change in voltage, you're going uphill, the change in voltage is plus IR. For a battery, this is the low voltage, that's the high voltage, change in voltage is plus V. When you're going in this direction, you're going from high to low voltage, it's minus V. Again, to solve a circuit problem, the number of equations one needs is equal to the number of unknown quantities. In this case, you have 3 unknowns, I1, I2, and I3. Okay. And so when we solve problems, you'll understand this better. Okay. All right, so that's the Kirchhoff's rules are the main main concept of this chapter. Okay, and now let's use this to solve some problems, solve some circuits. So here's a circuit. Okay. You learned this in physics 1. You will have a system. You want to study the system. And what is the best thing to do? Well, if you can do this, it's the cheapest thing to do. What you want to do is, and most of the time we are interested in systems that change with time, so dynamical systems. Okay? So what you want to do is come up with a mathematical model for it. Yep. And that mathematical model, more often than not, is a differential equation. Okay. So we want to describe the behavior of this system. Okay. So here is the circuit, and if the switch is open, nothing is happening. Nothing is changing with time. There's no need for an equation to describe that. Okay. What happens? Stuff starts happening once you close the switch. Yeah. So we're going to close the switch. That's time 0. And now things will change in the circuit, and we want to study them. You close the switch, and now, see, this is a complete circuit. What does Mr. Kirchhoff's second rule say? That the sum of the voltages around that loop should add up to 0. So we're going to use that rule. All right, so we're going to go around the loop. You can start at any point. You can go around in any direction. If you go around in this direction, you'll get an equation. And if you go in the opposite direction, you'll get the same equation with a minus sign. But if they all add up to 0, it doesn't matter. All right, so we'll go around the loop like this. Okay, so, and by the way, in that equation, you'll have as many terms as there are elements in the circuit. So in this loop, there are 3 elements. 1, 2, 3. You'll get three terms in that equation. Okay, so we're going to start here, go across there. When you go from here to there, you see the voltage changes E. And when you close the circuit, what is happening? This thing is charging. And what we are really solving for is Q is a function of time. The charge on the capacitor is building up, and that's what we want to know. Okay. So now this is at a higher voltage than that. Okay. So when you're going from here to there, and you guys remember the capacitance is charge divided by voltage. So voltage across the capacitor at a given time is the charge on the capacitor divided by C. Okay, so you are going from high to low voltage, and there is the negative minus Q over C. And again, this is function of time, which is what you're interested in finding. And as the capacitor is charging, as electrons are flowing, well, the current is flowing in this direction, and current is flowing. So now you're going across this element, you're going with the current, okay? So it's minus IR. So Mr. Kirchhoff's rule gave you this equation, minus ITR equal to 0. Now, the current in the circuit is the rate at which this thing is charging. So it's E minus QT by C. I is dQ by dt. All right, so the behavior of this system, okay, the time evolution of this system is governed by this differential equation. That's what Mr. Kirchhoff said. How do we know if Mr. Kirchhoff is right? Solve it. You know how to solve this equation, or you'll learn how to solve this equation. Okay, here's a solution to that equation. You solve that equation, and then what? Set up that circuit, test it in lab, measure the charge on it or voltage across the capacitor, and see if it agrees with this equation. If the measured value, if your experimental results are in agreement with the predicted results, then your assumption's correct. Yeah? In fact, we'll do this experiment. Okay. So there we go. Okay, so again, let me summarize this. And this is a common theme. You'll do this throughout your engineering life. You'll have a system. You'll come up with a mathematical model based on principles that you learn. The mathematical model has physics input or engineering input or whatever input. Okay, so your system, okay, so the flow diagram is as follows. System, some principle, mathematical model, and then the math that you learn will give you solution. Then you test against real system, okay? Good, no good, bad. Then you go back to the system, refine the principle, and so on. And you keep doing that till you get to good. All right, so you have a system, you come up with a model, and then solve for it, okay? And since we're teaching this to you in a course, the principle is correct, okay? So it does give correct results. So here's how the charge builds up on a capacitor. It's an exponential buildup, okay? This is called the time constant. The greater the time constant, slower the capacitor charges. Okay? So the time constant is RC. You guys might have heard of RC circuit, and that's where the name comes from. A resistor and a capacitor in the circuit. Okay? Greater the resistance in the circuit, slower it'll charge. Okay? And after one time constant, after t equal to RC, the capacitor will have charge to 65% its value. Okay? After one time constant. It's roughly 65% of its value. And as the capacitor is charging, the current in the circuit is falling down. Okay? And the current falls down exponentially with the same time constant. The current is just a time derivative of that. So you've seen this basic circuit. you close this switch and you charge the capacitor. Once the capacitor's charged, you open this circuit, and then you close this switch and discharge this energy through your load, whatever that might be. Okay, it could be a flash camera bulb, it could be your jump starting somebody's heart, it could be a pacemaker, okay, or any of the other things. So you charge the capacitor, and then you can discharge this through it could be a supercar, sports car, which has supercapacitors in them. Once you come to a red light, you store that energy, and then as soon as the light turns green, you can, this can be the turbocharger for your car, sort of, okay? So this is the basic circuit, okay? Now, we just learned about charging the capacitor. Now we'll come up with an equation for discharging the capacitor for this part of the circuit, okay? So, oops, I need to put a resistor here. So we're going to discharge this capacitor through your load. All right, so again, so now we're looking at the second half of the circuit. Okay. When the switch is open, you haven't taken a picture yet, you haven't clicked on the camera yet. Okay. So when you close the shutter, okay, or click the camera, now we want to see how things evolve. Okay. How the charge on this capacitor changes. Okay. So once you close this, you want to see how the charge changes. Okay, the capacitor discharges, passes a current through this guy. Okay, again, this is a closed loop, so Mr. Kirchhoff has something to say. He tells us that the sum of the voltages across all elements need to add up to 0. Yeah. So I guess the equation is set up where you're starting here and going around like that. Okay. When you go across this element, you're going from high to low voltage, so there's negative Q over C. And again, negative QT over C. And then you're going against the current, so it's plus IT plus ITR equal to 0. Here, in this circuit, I was equal to dq by dt. As the capacitor was charging, the current in the circuit was the rate at which the charge built up. Okay, so we know that I is related to Q, but look at this. Here, I is written as minus dq by dt. Here it was plus dq by dt. Here it's minus dq by dt. What's going on?
In the previous one, we were charging the capacitor, and this one we're discharging it.
Mm-hmm.
So the charge should go down.
Yes, so the charge is going down. There was an increasing function. I was dq by dt was positive, and I was equal to that. Here, the charge is, like you say, is decreasing. dq by dt is negative. Negative is positive. Okay. So that's what was going on. Okay. So there's the differential equation for the discharging capacitor. And again, here's the equation. This equation governs the rate at which the capacitor discharges. So here's the mathematical model. And again, you can solve this differential equation. And here's the solution. Okay. So what this says is that t equal to 0, that's the charge on the capacitor. So that was the maximum charge on the capacitor. And once you close the circuit, it's discharging. And it discharges exponentially. And again, the time constant is that. Okay, so you guys remember we saw in a lot of applications, you were taking a while in the flash camera application when the capacitor is charging, when that orange light is blinking, you charge the capacitor slowly and then you discharge it fast. So when you're discharging fast, the time constant is small. Okay, so the load resistance is small. Okay. And again, the current is also exponentially decreasing. So those were the main things from this chapter, principles. Okay, again, let me summarize them. In trying to solve circuits like this with multiple sources and multiple elements, you will need the Kirchhoff's rule to solve these circuits. This is the junction rule, and this is the voltage rule. Yeah. And then we use the voltage rule to solve circuits like this. Okay. All right, now let's look at a couple of applications. Okay. A pacemaker is, so a normal heart beats at regular intervals. Okay. The heart's own electrical signal regulates its beating. Okay. So you have a timing device, yeah, which lets you, makes your heart beat at a regular interval. So if that timing device goes bad or whatever, if for some reason the heart does not beat regularly, a pacemaker can be installed to maintain proper regular rhythm. Okay, so here is a circuit. Okay, so here is the battery. So that thing has this circuit and battery. Okay, and the battery, I don't know what they do these days, if you can wirelessly charge them or you have to replace the battery. But anyway, here's the battery through this resistance, and the heart is also a resistance. It charges the capacitor. Once the capacitor is charged, you have a timing device in that circuit. You have a timing device that will close the switch, and the capacitor will discharge through the heart. This is driving a larger current. While it's charging, that current is small, which cannot trigger the heartbeat. When you close the switch, you send a large current which triggers a heartbeat. Yeah. So, if you want 70 beats a minute, you close the switch 70 times a minute. Yep. And before you close the switch, you got to make sure that the capacitor is charged. Yep. So you close the switch and fire the heart. Okay. Nowadays, so let's say your pacemaker is set to beat at 70 beats a minute. You close that switch 70 times a minute. What if you go for a run? You have to make sure your heart beats faster, like 50 times a minute. So you got to figure out that timing device, to vary that timing device to close the switch 50 times a minute. Okay, or no, 100 times a minute. Yeah.
So I looked it up because I was kind of curious,
Mm.
and they don't have rechargeable batteries.
Okay.
So then when the thing dies, you got to go in and have surgery and have the whole thing replaced.
Right.
That's kind of crazy.
Yeah. So now those guys will. So if the surgery costs $20,000 You come up with a battery that's twice as long, you can sell the battery for $10,000. Yeah.
That's true.
Right. So that's the economics. All right, so that circuit shows up everywhere. Okay, here's an interesting problem. Here's an electrical. So, oops, let's do. Yeah. Here's an electrical eel. Here's a fish. The electrical eel will pass a 1 amp current through the fish dies. What is the current flowing through the electrical eel?
Not as high as it was in the fish.
It's 1 amp. 1 amp is flowing through the entire circuit.
Oh, the voltage is lower?
Hmm? So now you understand the problem. The question is, why is the fish dying and why isn't the electrical eel dying? So you got to kill something without dying. So how do you solve that problem?
Could be in parallel, so that looks like it's a parallel circuit.
It doesn't matter. Here's the 1 amp current flowing through the fish that killed it. And here's the same 1 amp current flowing through the eel.
Doesn't the voltage have to go down after the fish?
The voltage has to adjust such that in this circuit, in any circuit, it's the same current that's flowing.
You need to open the circuit.
Hmm?
You need to open the circuit. So
Then the current dies. The current doesn't flow. Then your food, you won't be eating that night.
current kills.
Hmm. So nature is very smart.
Does it have something to absorb the shock?
Okay, so here's what. So the question has gotten under your skin. You guys understand the question? Yep.
Does the electric eel have to be in contact with the fish?
No, this is a fish. Seawater is conductive. So I could be an electrical eel, you can be a fish, I could kill you. We both have to be underwater. All right, so here's how it solves the problem. You guys understand? So what it does is it breaks this current into, this current through the fish is flowing through this one path, okay? Inside the eel, it's broken up into 150 branches. So in each branch, 1/100th of a current is flowing. So if that small current flows through the heart of the eel, it doesn't kill it. This large current flows through the fish's heart. So goodbye. Okay? So that's how it solves the problem. Pretty crazy. Okay, so you guys have heard of biomimetics? I've mentioned this before. Bio. This is a branch of engineering. What does the word mean, you think?
Copying nature.
Okay, copying nature. You want a solution to an engineering problem, go look for how nature solved it. Yep, there's a solution. So here's a famous problem. If you guys see supersonic jets, here's the engine cowling, and you'll see a nose cone there. Okay. So when they were first designing supersonic jets, fast jets, here was the problem. You're going super fast, and what do you want as you go faster? What is it that you want?
Plane and not break apart.
You want to burn fuel at a higher and higher rate. You want more and more oxygen. You want more and more air coming through your cowling. The faster you're going, it turns out that there wasn't enough air coming up. It was almost like the air was going around. I guess pressure would build up and you were not getting enough air. That couldn't solve the problem. So one of the engineers studied a falcon. Those guys can dive at 200 miles an hour, and they were having no problems. And he noticed this cone in their nostrils. That's how it came about in the engine. Amazing. What? All right, so again, so here's the yield problem. So the batteries of an electrical, by the way, in every cell, the potential difference between, so the inside, we'll come to this in a second, it's about 70 millivolts, okay? So the inside of a cell is 70 millivolts below the outside. So that's the potential difference between all cells. So yields have this specialized cell where they're called electroplaques, and the EMF is 150 millivolts, so twice this volt. So an electroplaque is a cell where the voltage is 150 millivolts. And an internal resistance of 0.25 ohms. So there's the internal resistance, there's the cell, okay? Each eel has 140 rows of these guys. Each row has 5,000 plaques, so 5,000 batteries. And so, and each battery is 0.515 volts. And so the total voltage is 5,000 times that is 750 volts. So here's a 750 volt battery, and you're connecting 150 of them in parallel. So this, all their currents add up. Okay. So this array of electroplaques is 750 volts, and the internal resistance is 9 ohms. The yield uses the surrounding water to complete the circuit from near its head to tail. This amount of seawater has a resistance of 800 ohms, so the resistance is 800 ohms, through which a current of 1 amp can be passed. So you can pass a current of 1 amp through that fish. And then once the current comes back, what is passing through each branch of the eel is 1/50th of that current, 1/50th an amp. So this current doesn't do damage to the eel. A current of 1 amp passing through a fish swimming nearby can kill it. Current in each of the electroplaque itself is 1/40th of that, or 6 milliamps. I don't know if you guys have seen these 3-way lamps. So when you close this switch, it acts like a 100-watt bulb. When you close this switch, it acts like a 75-watt bulb. And when both switches are closed, it's like a 175-watt bulb. Okay, so you're getting a live line and a ground wire from the power company, and there'll be a fuse. Each appliance is connected in parallel, and houses are connected in parallel as well. So for your heavy duty appliances, you have 2 live wires, and they're 180 degrees out of phase. So one live wire will carry a voltage like that, and the other live wire will carry a voltage like this, 180 degrees out of phase. So you'll get 240 volts between these two guys. Yeah. So for your washing machine and clothes dryer, you'll need that. All right, so we saw some applications, and if you want to hear about how a nerve impulse works, I can tell you that, otherwise we can stop. Stop?
Yeah, let's stop.
No. Does anybody want to hear about the neurons? Okay. Right, so each of us is born with about 90 billion neurons. So the hardware is the same. Okay, so we are all very, very capable. Yes. So the hardware is the same. When you learn something, what is it that you're doing? How do you make this network work better?
Make more connections.
What's that?
Make more connections.
Make more connections. The more connections you have, the better the network works. That's all you're doing. Okay? And, if you don't want to improve the network, you don't have to make connections. All right, so I'll keep things simple. So the first thing we'll do is, so I'm going to draw different kinds of diagrams. So here's a cell. This is the cell wall. There's the outside of the cell wall. Inside the cell, the voltage is minus 70 millivolts. Okay, so that's assuming, so we are saying this is 0 volts and this is minus 70 millivolts. So now we'll first see how this is generated. Okay, how you get negative voltage inside the cell. Yeah. So here's what's going on inside the cell. So here's that wall. Inside this cell, you have potassium ionic molecule where the negative molecule is large. Negative ion is large and potassium is the positive ion. Outside is seawater, essentially, outside your cell. It's potassium, it's sodium chloride. Your wall is semi-permeable. What does semi-permeable mean? I'm sorry?
Certain things can enter.
Yeah, it's selectively permeable. Okay? Okay, so in the resting stage, when nothing is being done, in the resting stage, it's permeable to, it'll freely let potassium ions go out. And we'll say it doesn't let sodium. So we'll keep it simple. Right now, we'll say potassium ions can go out. Okay, so in the resting state. Okay, and here's a diffusion is a random process. Okay, so what happens is if you have a higher concentration of potassium ions here, and if this cell membrane is permeable, randomly potassium ions will leak out. Okay, potassium ions will leak out. A bunch are here, and it's become positive. This thing has become positive because initially this was negative, and now you added a bunch of potassium ions, this becomes positive. Okay, so there are still potassium ions trying to get out, but these potassium positive charge will prevent them from coming out. Okay, so the equilibrium condition is some of these potassium ions have leaked out, this has become positive, and this region has become negative, and that equilibrium is minus 70 millivolts. Okay. All right, so let's come here. So you have excess potassium ions here. I mean, you have a whole bunch of potassium ions here, but so these are the negative large molecules. Okay. So there's the negative 70 millivolts. Okay. Now we'll do this in a nerve cell. So now this is the axon, which is inside a cell. This is minus 70 millivolts. This is the resting potential. Okay. Now let's say you do something here to the cell wall. You have to change its property. Remember, in the resting condition, all it lets through is potassium. Now let's do something. Let's change its potential. Let's pinch ourselves. What you did was you changed the membrane property here such that now you made holes where sodium ions can get in. So you're changing the property of the cell wall, and now you're making it permeable to sodium. Remember, this was positive, so sodium ions will come in here. They'll flow in till this potential becomes 0. That in that local region. They come in, so it becomes 0. Okay? So you change the membrane property, sodium ions flowed in, and the potential went to 0, or it went to plus 20 millivolts. Okay, once sodium ions come in, it's become plus 20, and so it'll force out more potassium ions. Okay, and so near that region, the potential goes back to. Okay, so all this happens very fast. It happens within 3 milliseconds. This is a nerve impulse. Okay. And when this happens, so what happened was you change the property here by pinching, ions flowed, and these flow changes the property here, and so that effect travels down the nerve. That travels down the axon. And it travels down the axon at 100 meters per second. Your nerve impulse will travel from here to the student center in 1 second. Okay. Now, what do you have to do once this nerve impulse travels? What do you have to do to get ready for the next pinch? Reset. So what do you have to do?
Go back to negative 70 millivolts.
You got to go back. You had a bunch of potassium ion, excess potassium ion, and bunch of sodium ions here. You have to take these sodium ions and put them back there. You got to bring these guys back here. Those are the ion pumps. 20% of your energy is spent on that. All right. So that's the nerve impulse, and that's how it travels. I pinched harder. How does my body know the difference? The nerve impulse it's the same amplitude. So the way we tell the difference is the frequency. If you pinch softly, you get 10 impulses traveling per second. 10 impulses generated per second. A harder pinch is 50 impulses per second. Okay. Okay. Okay, so nerve impulses travel along the axon at about 100 meters per second. Strength of signal is conveyed by the number of pulses transmitted.